Hello everyone, this is our video on energy conservation. Quick overview, we're going to be going over kinetic energy, potential energy, mechanical energy, and a few examples of how to use the mechanical energy formula to solve problems. Let's get started. Alright, so first of all we have our kinetic energy formula. Obviously kinetic energy is the energy of motion. We have our equation right here, kinetic energy is equal to 1/2 mass times velocity squared, where mass is in kilograms and velocity is in meters per second. Also, don't forget that once you use this equation and plug in the numbers, the unit for energy is always in joules. All right, moving on. We have potential energy. It's the energy stored, and it's dependent on where the mass is located in space. We have our equation right here. Potential energy is equal to mass times gravitational acceleration constant times height. Mass is always going to be in kilograms. G is a constant, like I said, so it's 9.8 meters per second squared. This is just a dash. It's not always negative. And H is your height off of the ground in meters. All right, so now we have mechanical energy. So mechanical energy is basically this idea that goes off of the first law of thermodynamics, that energy in an isolated system is constant. And so we're going to go to this analogy right here. This is like the yin and yang idea. This is actually taken from the TV show Avatar, if anybody's ever seen that. But it's basically that all the energy in the universe, right here depicted by good and evil, is like balance. It balances itself. So as we know, energy can just be converted into different forms. It cannot be created or destroyed. So all the energy is going to exist as either good or bad energy, right? So the same is in physics. The potential energy plus the kinetic energy added together must always equal the same value. So for our purposes, we're going to pretend that the white fish is potential energy, that the black fish represents kinetic energy. So right here we have our pool, right? Let's pretend in the pool, in total, we have 100 joules of energy, right? Now, this can be split between the two fish in any given way, as long as you add it up to 100 joules, right? So it could be split 50-50, it could be 30-70, it could be 60-40, right? And the way to solve for this type of energy, the potential energy, is given by this equation. And the way to solve for this type of energy is given with this equation. And so we have this equation here, the total energy, energy of mechanical or mechanical energy, is equal to the kinetic energy, which is represented by a big K, plus all the potential energy, which is represented by a U. Another way of representing this is you can represent this through algebra as mechanical energy must always equal mechanical energy. It will always equal itself. So you can rewrite this. You can replace the EM is equal to EM by K plus U. So kinetic energy initial plus potential energy initial must be equal to kinetic energy final, pretend there's a little f here, plus potential energy final. Another way of thinking about this is the change in the kinetic energy plus the change in the potential energy must be equal to 0, right? So if you add up the way that they change, there has to be no total change because we will always have the same amount, or like 100 joules. So just to put that into reference really quick, so let's say, all right, so we're split 50-50. The energy changes. So this one goes down 20. So this one goes negative 20 is the change. Over here, we go from 50 to 70. We have a plus 20 change. Well, if you add the changes together, we had a negative 20 right here. We had a positive 20 right here. We get 0. There's no net change in the total energy of the system. It's constant. So that's the main idea here with mechanical energy. All right, we're going to move on to an example. All right, so here's our example. We have this block right here. It's 2 kilograms, and the problem is telling us it's moving 10 meters per second to the right. So then you can see we have like this little hill, and we have that it goes up by 4 meters. And so the question is, what is the final velocity? So let's remember that the total energy must remain constant, and you can look back at the equations, but it's kinetic energy initial plus potential energy initial must be equal to kinetic energy final plus potential energy final. So let's find what we know first, right? We want to define everything that we know. So we know that the mass is 2 kilograms. We know that the velocity here is 10 meters per second. We know that the height off the ground here is 0, sitting on the original location of the ground, right? Up here, we know that the height is going to be 4. The mass of the block isn't going to change. It's going to be 2 kilograms again. And we just don't know the velocity. So I encourage you to pause the video, write out the equation really quick, define your unknowns, and then try and solve. So remember, we're trying to find the white fish here plus the black fish must be equal to the white fish plus the black fish. The kinetic energy plus the potential energy must be equal to the potential energy plus the kinetic energy over here, and you set them equal to each other basically. All right, so try that out, pause it really quick. Next slide is going to be the answers. All right, so here we are. So we have our white fish and our black fish over here. White fish, black fish. So find the velocity of each box, right? So this is what we know. We have the energy initially, right here of this block, is going to be the potential energy plus the kinetic energy. And so here are our two formulas. So we set that up. The potential energy is going to be mass times gravity times height. Well, height is 0, so this just becomes 0. And then over here we have our kinetic energy. So right now, what this is basically saying, if potential energy is 0, all the energy in the cube is going to be kinetic energy, right? So we move on to our energy final, which is the box when it's over here. We have our potential energy plus kinetic energy, right? So now we have a potential energy. It went up 4 meters. The height is no longer 0. So we plug in our numbers right here, plus, and then this is what we know. We don't know the velocity, but this is the equation, right? 1/2 times mass. We know the mass is still going to be 2. We don't know the velocity. That's what we're solving for. So then right here, we set the two equations equal to each other. EI must be equal to EF. So we take our EI right here, we put it right here, is equal to EF. We put it on the other side, right? So then we do all this math and we combine like terms. So over here on the left, once we do all this math, we have 100 is equal to this value right here. When you multiply this out, you get 78.4 plus velocity squared right here. The 1/2 times 2, that becomes 1. We're left with velocity squared. So then you can subtract this from both sides. We're left with velocity squared is equal to 21.6. And then you take the square root of both sides. We get the velocity is 4.64. I forgot to put units here. Velocity is always in meters per second. So we know that the box is moving to the right at 4.64 meters per second. So the other thing that we can look at here is we can look at the total energy if we were to write it all out, right? So the potential energy was 0, it's on the ground, 100 right here. Well, when we solve for each of these values right here, if you take these numbers, the E final, the potential energy final, and the kinetic energy final, and put them separately, look, the potential energy plus kinetic energy is equal to 100. If you add these two numbers together, we get 100. The total energy in the system did not change, it's constant. So that's about it for our video on energy conservation. Thank you.